All right, so last week we finished up talking about the role of the nucleophile in substitution reactions. And we said in SN1 reactions, the nucleophile really doesn't matter. And in fact, because it doesn't matter, you can get away with using a really poor nucleophile. So even in this example, we said that bromide is less stable and should be a better nucleophile, but the reaction rate for A and B is going to be pretty much the same because the nucleophile is not involved in the rate limiting step. With SN2 reactions, on the other hand, nucleophile strength plays a critical and important role. Not only its concentration, but its instability and sterics. So in this first example, we said bromide is less stable and therefore a better nucleophile. However, I had an important caveat that solvent affects all of this, right? And so that's what we're going to talk about today, is the role of solvent in these reactions. And it can be a bit confusing. All right, so let's consider the transition state. And I'm going to abbreviate transition state TS double dagger for SN1 and SN2. Yep.
Did we talk about leaving group importance yet?
Not yet. We will get there, though.
We're skipping that on the boxes and come back to it.
We're going to come back to that. Yeah, exactly. All right, so let's go consider this part. So the transition state for SN1 involves what bond being made or broken? What does it look like? What's the rate limiting step? Leaving group falling off. All right, so if we consider it for SN1, all right, we might have something that looks like this. I'm just going to make up an example molecule. And in this example, my leaving group is an iodide. So I'm going to show that as delta negative. The carbon is becoming a carbocation, so I'm going to show that as partial positive. All right, we'll do the same thing with SN2. SN2 reactions, we said, are much more likely to occur not with tertiary carbons, like the example with SN1, but much more likely to occur with methyl or primary carbocations. And in this example, I'm going to show it a little bit differently. I'm going to use a methyl electrophile. And on one side, our leaving group is getting shoved off. And on the back face, our nucleophile is attacking in. So our nucleophile is delta negative, our leaving group's delta negative. And we said that this is a trigonal bipyramidal transition state. All right, so if we look at each of these transition states, there's a pretty extreme dipole going on, right? There's not a shared balance of electron density. The net imbalance is quite apparent because we have partial charges, right? So let's make a note of that. So both transition states are polarized. Meaning there's an imbalance of electron density. If we think about wanting to speed up this reaction, would we prefer to have a more stable transition state or a less stable transition state? Ooh, let's think about it, right? So let's compare both of these. And I'm just going to use a generic hump for an SN2 reaction. We're not changing the starting materials or products. We're only considering the transition states, right? So let's say we've got a blue pathway with a higher transition state energy than this green pathway that's lower. Which reaction is going to be faster, the green pathway or the blue pathway? Green one, right? So in this one, we would say the green pathway is faster due to a more stable transition state. So when we're trying to do these substitution reactions, one way of increasing the reaction rate is to try to stabilize that transition state in some way, shape, or form. That way the hill is less extreme that it has to climb, right? All right, so if we think about these polarized transition state, the question is, how can we stabilize a polarized transition state? what sort of solvent do you think might stabilize a polar transition state? A polar solvent or a non-polar solvent? Polar solvent, right? We know from general chemistry and even earlier this year that dipole-dipole interactions stabilize one another through kind of this docking mechanism. That's the exact same thing that occurs here. So a polar solvent will stabilize these transition states and allow both SN1 reactions and SN2 reactions to occur faster. So let's make a note. For both SN1 and SN2, leading to a faster, slash more likely, or actually I should say faster or more favorable reaction. All right, so in general, when we're running substitution reactions, we avoid nonpolar solvents like hexane. Any hydrocarbon-based solvent we typically avoid. We want something with a pretty strong net permanent dipole, right? Solvents that only have dispersion forces typically destabilize that transition state and will actually make the reaction not occur as fast, or it will prevent it altogether. Yeah?
So, taking that initial compound from the pod from today,
yeah.
If we actually wanted to keep it like that, would we store it in a non-polar solvent, or?
Yeah, so if you isolate it by itself and it's not in solvent, sometimes it'll just stay put. So one way of preventing substitution is don't let it touch solvent or a potential source of a nucleophile. Yeah. All right, so polar solvents come in a wide variety of types, right? I forgot my handout, but do you remember the handout I gave you with common organic solvents on it? And I had 3 main categories. I had common non-polar solvents, and then I had polar aprotic and polar protic solvents. I think I gave it back to you back in the acid-base chapter. But let's go talk about the difference between those. All right, so polar protic solvents we'll put on the left. And then we'll put polar aprotic on the right. Okay, if we think about a polar protic solvent, the big clue here is pro. That implies that there's protons, specifically protons that can hydrogen bond, right? So polar protic solvents can H bond. Polar aprotic solvents cannot H bond. And so oftentimes students will look at this and they'll say, well, if we're trying to stabilize the transition state, shouldn't we always go with polar protic solvents? Not entirely. We have to consider a bunch of other features as well. But let's take a look at what's going on between the solvent and the nucleophile in each of these. So the best example we have of a polar protic solvent is water. It's one of the cheapest, most readily available solvents. And if you have a nucleophile with a negative charge floating around, actually let me make this a circle. That water molecule is basically going to hydrogen bond to that anion, right? If the nucleophile has a negative charge. Essentially, you're just going to have a bunch of water molecules wrapping up this nucleophile through H bonding. Oop. In fact, depending on the sizes of the nucleophile, a lot of water molecules can actually squeeze in close and form a 3-dimensional shell around an entire nucleophile, right? So hydrogen bonding in this case, do you think it's stabilizing or destabilizing the nucleophile? Stabilizing, okay? So let's make some notes. So the nucleophile can H bond to protic solvents. This stabilizes the nucleophile. All right, if we think about SN1 and SN2 reactions though, well, let's actually back up. Let's consider an SN2 reaction. Is this beneficial to have a stable nucleophile? No, we said in SN2 reactions, we actually wanted an unstable nucleophile that would aggressively attack the substrate and kick off that leaving group, right? If it has a shell of water, hydrogen bonding around it, it's essentially wrapped up and it's going to be a lot less accessible for attack. So polar protic solvents generally aren't desirable for SN2 reactions. So let me zoom out a bit. So polar protic solvents are generally not desirable for SN2. Let me clean up my knot there.
Generally we're going to have to be worried about?
So there are some situations where that generally term does come into play. So what I always tell students is don't use solvents to predict whether or not a reaction is going to be SN1 or SN2. Solvents just play a supporting role, right? So they're kind of another thing we might want to look at, but they're not going to be the primary thing determining whether or not a reaction is SN1 or SN2. All right, let's consider polar aprotic molecules. Same idea. We're going to have a nucleophile kind of in the middle there. But a polar aprotic solvent cannot H-bond. Instead, it's going to want to put its partial positive end closer to that negative charge on the nucleophile. So if we have a molecule like acetone as our solvent, right? Acetone has this big net dipole going up towards the oxygen. So basically, the legs of the acetone are going to be kind of pointed towards the nucleophile. And it's going to wrap up that nucleophile in a similar manner, but a lot less tightly, right? Because it can't H-bond. Okay, so in this example, let's make a side note that the nucleophile cannot H-bond to the solvent. And is wrapped up less tightly. Do you think that stabilizes the nucleophile relative to the polar protic solvent or destabilizes it? It's going to destabilize it, right? If you're hydrogen bonding with your solvent as a nucleophile, you're going to be wrapped up very tightly in this comfortable wall of hydrogen bonding blanket, right? With a polar aprotic solvent, you're being held a lot less tightly. You're a lot more vulnerable to one of those acetone molecules being ripped away from you. So this destabilizes the nucleophile. So let's actually underline this and say less stable on the polar aprotic side, more stable with H bonding. All right, so if we think about polar aprotic solvents, these are actually pretty good for SN2 reactions. We want to destabilize our nucleophile. We don't want it to be wrapped up by our solvent. We want it to be able to attack our electrophile. So they are good for SN2. Yep.
When you say the nucleophile is less stable, is that in comparison to if it were in a polar protic solvent or?
Yes. Yeah, so the question is, was the comparison to a nucleophile in polar protic solvent? Yes. So what we're comparing is polar protic to polar aprotic. When you're in an aprotic solvent, you're going to be solvated less tightly. That means your nucleophiles got to carry that burden of the negative charge without the support of H bonding to stabilize it. That means your nucleophile is going to be a lot more unhappy and a lot more aggressive about finding an electrophile. Does that make sense?
Yeah.
All right, so then the question students will often ask is they're like, all right, so in the example on the right, the nucleophile is less stable. It's going to be a lot more aggressive about attacking an electrophile. Why don't we just run all substitution reactions in polar aprotic solvents? Does anybody know?
Sometimes the transition state's not as stable in polar approach.
Not quite. I think that's a reasonable guess. So you're talking about transition states. It could be cheaper. Does the nucleophile play a role in SN1 reactions that really is meaningful? No. So we were looking at nucleophiles here. We only really look at nucleophile strength with SN2 reactions, but you were on the right track with the transition state. So let's go back and talk about that. So let's consider SN1 reactions. So the nucleophile doesn't matter as much because it is not involved in the rate limiting step. And I'm going to call rate limiting step RLS. And instead, the rate limiting step is what?
Question.
Yeah.
It doesn't matter as much, or it doesn't matter?
So when I say doesn't matter, the concentration doesn't matter at all in terms of the reaction rate. So what I'm referring to is the rate of the reaction doesn't really matter for a nucleophile. You still need a lone pair to have a nucleophile, right? So you've got to be able to have some electrons to donate in order to be a suitable nucleophile. All right, what's the rate limiting step for SN1? Leaving group falling off. All right, let's make a couple of side notes. In the previous example, the way we actually made the reaction speed up was destabilizing our starting material. By destabilizing our nucleophile, in effect, we lowered the hump that had to be overcome, right? In this one, we're not going to be able to destabilize our starting material. So let's just put that down. So solvent doesn't really destabilize the starting material. In SN1 reactions. However, it does lower the transition state energy. Oh, come on. Is my eraser going to work? All right, so let's consider this SN1 reaction. And in an SN1 reaction, like we said, I'm going to just redraw it down here. The transition state involves the leaving group kind of falling off. I'm just going to put this in a double dagger, include my partial charge on my leaving group and my partial charge on my carbon. So now the question is, what's going to stabilize this transition state more? A hydrogen bonding solvent or an aprotic solvent? Hydrogen bonding, why? H bond stronger, and H bond is essentially going to stabilize this transition state, which in this case is what really matters. So let's make a note of this. We want a solvent that will stabilize the leaving group falling off and in this case, polar protic solvents, can H bond to the leaving group as it falls off. So in an SN1 reaction, polar protic solvents are actually more favorable because they essentially catch that leaving group as it's falling off and stabilize the transition state. Yeah?
So essentially H bonding always does the stabilizing, it's just a matter of if the reaction wants stabilizing.
Yeah, exactly. If we're looking at an SN1 reaction, our goal was to stabilize the transition state. So we still did want a polar solvent. However, on the flip side of that, we wanted to destabilize our nucleophile, which is more favorable in an aprotic solvent. In the lower example with SN1 reactions, we said the nucleophile doesn't matter. In fact, destabilizing it doesn't help us in any way, shape, or form. So instead, we just want to stabilize our transition state as much as humanly possible, which is going to be achieved with polar protic solvents. Yeah, great questions. So let's just write this down. So polar aprotic is best for SN2. Polar protic is best for SN1. And I'm going to even make a note off of this one. In SN1 reactions, your solvent is often your nucleophile. It's a little bit weird to think about, right? But if you've got a polar protic solvent, that polar protic solvent has lone pairs that can attack in, like we saw in our problem of the day. Water is a good example of that. So water can be both a solvent and a nucleophile. So why complicate things? Why not just make your solvent your nucleophile? So oftentimes that's the case in SN1 reactions, but it's not always the case. So you might always want to consider all of your potential options. Does that make sense? Yeah.
So you're saying on the note that polar aprotic is best for SN2, but you just finished explaining that it doesn't actually matter.
So up here, we were talking about SN1 reactions. Yeah. So in SN1 reactions, we said destabilizing your nucleophile doesn't matter because it doesn't impact the rate. However, lowering the transition state energy does help you. So our goal in SN1 is to stabilize the transition state, not destabilize our nucleophile. Yeah, so there is a lot of stuff to pay attention to here. So now let's go back and consider some trends. So I'm just going to make this deeper down the rabbit hole. dot, dot, dot. Going to make everyone's head spin. Let's consider some competing nucleophiles, right? So I'm going to have hydroxide as a nucleophile. That's pretty good. I'm going to have a thiolate as a nucleophile, and then the selenium analog. All right, which is more basic? Hydroxide up top or the selenium compound down below? More basic. All right, let's back up. Which one's most stable, top or bottom? All right, so bottom's more stable. And why is the bottom more stable? Yeah, atomic size. All right, so when we think about a good base, should a good base be something that's really stable and happy or something that's unstable and wants to steal a proton? Unstable. All right, so I'm going to put that up here. More basic. All right, now we need to consider nucleophile strength. All right. Up here in red, let's consider an aprotic solvent. These are more nucleophilic and aprotic solvents. basically we said that an aprotic solvent, yeah, it kind of hangs on to the nucleophile, but doesn't do a very good job at it. So in aprotic solvents, we basically follow the same trends as with basicity, right? The less stable your nucleophile is, the better it's going to be at attacking something. All right? However, let's consider hydrogen bonding. All right, with hydrogen bonding, which one do you think is going to be the best at hydrogen bonding with a protic solvent? OH, right? So if you think about OH as being really, really good at hydrogen bonding, the hydroxide anion, does that mean it's going to be a good nucleophile in a hydrogen bonding solvent? No. So down here, this is more nucleophilic in polar protic solvents. Simply because the hydrogen bonding just simply isn't as tight. You've got a giant selenium atom with a negative charge. It's going to be a lot harder to hydrogen bond with. Yep.
And if you really screw up your nucleophile and solvent, you're going to end up doing acid-base instead of substitution, right?
Yeah, we will talk about acid-base chemistry when we get into the second half of this chapter with elimination reactions, and that's where this will come back again. So it's not going away. Yeah.
And by when you say more nucleophilic, you mean thereby more willing and able to do nucleophilic attacks.
Yeah, exactly. When I say more nucleophilic, I mean more capable and ready to do a nucleophilic attack. That big old selenium atom can't H-bond very well with a polar protic solvent. Therefore, it's going to be ready and willing to work as a nucleophile.
Okay.
Yeah, so we've got all these competing trends we've got to consider, right? We've got basicity, we've got stability, we've got nucleophilicity in aprotic solvents, we've got nucleophilicity in protic solvents. It's kind of confusing, right? The big thing I remember is an aprotic solvent essentially only stabilizes your transition state, but it destabilizes your nucleophile. It's the exact same trend as basicity. However, with polar protic solvents, the trends are reversed. All right, now let's do the next one. Actually, let me change this. What about nucleophiles in the same row? All right, so I'll kind of show you what I mean by this. Let's do NH2 versus OH versus F minus. Which one's more stable? Fluoride. Okay. And that's due to electronegativity trends, right? So when we looked at atoms in the periodic table, we said if they're in the same row, we have to look at electronegativity. If they're in the same column, we look at atomic size. All right. Which one do you think is going to be a better nucleophile then? NH2? All right, if we look at these ones though, do we need to really consider polar protic versus polar aprotic? Well, maybe. Let's consider it, right? Let's consider we have something that can hydrogen bond. All right, if you have something that can hydrogen bond, which would it prefer to hydrogen bond with? F minus or NH2 minus? I'd say F minus, right? It's got that full negative charge. It's a really small atom too, so it's going to hydrogen bond pretty tightly. So again, that makes F minus a pretty crummy nucleophile in a polar protic solvent. What about a polar aprotic solvent? Then we just follow our basicity trends, right? So really, solvent doesn't play a role as you go across a row. It doesn't play a role as you go across a row. It only impacts as you go up and down a column. So let's make a note. So polar protic versus aprotic. Doesn't really matter here. All right. Now we've hit our negatively charged nucleophiles going up and down a column, left and right across the row. However, sometimes we have nucleophiles that simply have no charge too. So let's consider some of those. So what about neutral nucleophiles? Yeah, so we're looking at SN2 reactions primarily with these. So solvent plays a really important role with SN2, but like we said with SN1, our solvent choice does matter a lot, and this next part will feed into that as well. All right, so let's consider the following. Oops, sorry, this should be a CH2, CH3. So these are pretty analogous nucleophiles, right? They're both neutral, and in this case, they could both act as your solvent, right? All right, which of these do you think is going to be more capable of acting as a nucleophile? Check with your neighbor and see if you can agree. So assume you've got either pure ethanol or pure thioethanol, or ethane thiol. Yep. It's similar. There's a bit more going on too. All right, so this one's kind of abstract. So let me see if I can guide you. Which of these can hydrogen bond? The top one or the bottom one? Top one. Okay, so the top one can H bond. So let's make a note. This can H bond. What is it going to H bond with? With itself, right? It's just going to H bond to itself in a cluster. The bottom one essentially can't H bond. So knowing that the top one will H bond tightly to itself, is the top one going to be a very good nucleophile? Top one's probably not going to be a good nucleophile because it's H bonding together in a cluster pretty tightly. The bottom one is just held together through dipole-dipole forces. That means that this is a better nucleophile. Okay, so basically when we look at this, we get more nucleophilic as you go down a column. Right? The closer we are up to the top of a column, the less nucleophilic things tend to be because they're neutral and they tend to H bond to themselves or at least have stronger electrostatic interactions. Yeah?
Does that only count for neutral nucleophiles?
Yes, this is only true for neutral nucleophiles. And in this case, these are neutral molecules, so they're typically their solvent too. So we just run these in pure, like say ethanol, for example. All right, one last one, because I know it's not complicated enough yet. Let's compare water. So let's do this. What about if they are in the same row? We just did the column. So up and down, right? Sulfur and... Yeah. So what if they're neutral and in the same column? Or row. Holy cow. No, you're helping me out. The same row. All right, so let's compare two easy ones. We've got water versus ammonia. Well, both of these can H bond, right? We're kind of in a pickle. All right, now the question is, well, which one's going to act as a better nucleophile, water or ammonia, and why? Think about it this way, too. A nucleophile, when you're talking about a neutral nucleophile, is donating one of its lone pairs to the electrophile, right? Which one's more willing to donate a lone pair? Oxygen or nitrogen? Check with your neighbor and see if you agree. I want a good argument out of this. All right, so let's talk about this as a class now. If we're looking at a neutral nucleophile in the same row and we're asking which of these lone pairs is going to be more accessible to be donated, the lone pair off of oxygen or a lone pair off of nitrogen, what do you think? Does anybody want to share? You think nitrogen? Why?
Because oxygen is more electronegative than what's more.
Yeah, so as you were saying, oxygen's more electronegative. It's going to hold its electrons close, right? Those lone pairs are going to be held tightly by that electronegative oxygen. Nitrogen's way less electronegative, so its lone pair cloud's going to be sticking out further and a lot more available to act as a nucleophile. So I think that's a perfect explanation. So less electronegative equals lone pair held less tightly. That means as we go across a row, we actually get more nucleophilic as we go left to right. So this would be more. Or do I have nitrogen in the right spot? No. I'm completely flip-flopping these. This is going to confuse me. So I'm going to take this. Sorry. These are in the same row, more in this orientation. I should have had that flip-flop before. This is what happens when I freewheel on my notes. These are more nucleophilic because they're less electronegative as we go left to right. So there's a lot going on with solvents. My main takeaway, though, is when you go to that main chart that I gave you, look at solvents essentially last. Don't use solvents as a predictor of whether or not something's going to be SN1 or SN2. But if you're trying to dive into the nitty-gritty details of a reaction, definitely look at solvents and determine, all right, is this solvent more favorable for SN1 or SN2? Yep.
So where we should look first is whether how likely a weak is to fall off. Is that your turn?
Yeah, so if we go to our decision-making flowchart, right, the things we have filled in so far are the most important. Arguably, the substrate is the first thing I look at. So if the thing with your leaving group is methyl or primary, we know it's likely going to be SN1, right? Because those don't form good carbocations. Whereas if it's resonance stabilized or tertiary, we know it's likely going to be SN1, not SN2. The question is, well, what if we've got a secondary carbon? That could go either way because it's in the middle, right? That's when we might look at solvent as kind of this tiebreaker situation to predict whether or not something will be SN1 or SN2. Yep.
So could the same compound be SN1 in one solvent, SN2 in a different solvent?
Yes, exactly. So sometimes if you're dealing with a secondary substrate, it'll be SN2 in one solvent and SN1 in another solvent. Great questions. All right, so the problem of the day for tomorrow is asking about leaving groups. I think you have enough information to figure that out just based on your own intuition, but if you do get stuck, feel free to email me. Think about the transition state for that reaction.